Welcome to the deep dive.
Glad to be here.
So today we're jumping into some really fundamental ideas from geometry.
Symmetry, reflection, and rotation.
Yeah.
Foundational stuff.
Exactly. You've shared some excellent source material. And, well, our goal is to really unpack these concepts.
Yeah, get beyond just definitions. See how folding, mirroring, and turning actually describe how things relate in space.
Right. How these simple actions work. Okay, let's dive in. Where should we start? Symmetry.
Sounds good. Symmetry first. The basic idea, as the sources put it, is about folding.
Ah, the fold test.
Mm-hmm.
If you fold a figure along a line, the axis of symmetry, the two parts have to match up perfectly.
Precisely. It's about this kind of inherent balance within a shape, and, the number of these lines tells you quite a bit.
Right, and the sources give good examples, like triangles show this off really well.
A scaling triangle, no equal sides.
No lines of symmetry, you just can't fold it onto itself evenly.
But then an isosceles triangle, with its two equal sides, it has that one line.
Just one, straight down the middle from the unique angle to the base.
Yeah. And then the equilateral triangle. This is where it gets really interesting based on your notes.
3 lines. And they're not just symmetry lines.
No, they're doing double, even triple duty. They're angle bisectors and they're perpendicular bisectors of the sides.
It really shows that deep connection between symmetry and other properties in those very regular shapes.
Absolutely. And quadrilaterals, well, they broaden the picture even more.
Okay, so surprisingly, maybe a parallelogram has 0 lines of symmetry.
That's right. Try folding one, it won't work. But a rectangle gets 2.
Down the middle, horizontally and vertically, and a rhombus also gets 2.
Yep, but along its diagonals instead.
And the square, being so regular, it gets 4, both the midlines and the diagonals.
It maxes out its sides. And the sources also mention others, like an isosceles trapezium has one. A kite shape too, just one.
Then there's the circle. Infinite lines of symmetry. Any line right through the center works.
Which leads to that pattern the sources point out. For a regular polygon with insides, the maximum number of symmetry lines is n. It's a nice, clean rule.
Okay, so that's symmetry within a shape. Now, reflection, that's symmetry across a line, like looking in a mirror.
Exactly. The sources describe it geometrically. Yeah. Take a point P, reflect it across a line AB, and you get P prime.
And the key is that the line AB cuts the segment PP prime exactly in half.
And at a right angle. Perpendicularly bisected. That's the crucial part.
So how did this play out on, say, a coordinate plane? That seems important.
It is, and the sources give us these really elegant rules. Reflecting a point xy across the x-axis.
You just flip the sign of the y-coordinate, it becomes xy.
Simple as that. And across the y-axis.
Where it's the x-coordinate sign xy.
Right, and if you reflect through the origin, the point 0...
Both signs flip.
Okay.
It's amazing how these simple sign changes capture that mirroring effect perfectly. Like the example 5-4 reflected in the x-axis becomes 5-4.
Very neat. Okay, last one. Rotation. Turning things around. Yeah, this is about pivoting a figure around a specific point, the center of rotation.
And the big takeaway from the sources here seems to be that rotation doesn't change the shape or size at all.
Correct. It's what we call a rigid transformation. The angles, the side lengths, they all stay exactly the same. You just change its orientation.
So you need that center point, an angle to turn by, and a direction clockwise or anti-clockwise.
That's all it takes. The figure itself is congruent to the original, just spun around.
Yeah.
It's fundamental for describing anything that turns or spins.
Okay, so we've really dug into symmetry, reflection, and rotation based on your sources. Folding, mirroring, turning.
Yeah, these simple actions reveal so much about shapes and space. And they're not just, abstract math concepts.
No, absolutely not. You see them everywhere. Art, design, physics, engineering.
Computer graphics rely heavily on reflection and rotation. Crystallography is all about symmetry.
Think about that maximum symmetry rule for polygons, or how just changing a sign gives you a perfect mirror image on a graph.
It's a powerful stuff. Which, maybe, leads to a final thought for you, the listener.
Right. As you go about your day, where else do you notice these ideas?
Where can you spot symmetry, reflection, or rotation maybe in places you haven't thought about before? It could be nature, architecture, even just everyday objects. Keep an eye out.